Thank you for watching this video. My name is Yui Sudo from Honda Research Institute, Japan. I'll present our research entitled Online Adaptation of Fourier Series-Based Acoustic Transfer Function Model to Improve Sound Source Localization and Separation. Robot audition techniques such as sound source localization and separation are essential to realize human-robot interaction in a real environment. In recent years, many deep learning-based methods have been actively proposed, but they are impractical for robots due to the high computational complexity. So transfer function-based array signal processing approaches are still important. Transfer function represents a signal propagation characteristics from a sound source to a microphone. To perform localization and separation based on array signal processing, a TF set consisting of multiple TFs is required for each sound source direction and microphone. Generally, a TF set is calculated geometrically or pre-measured and fixed, so environmental changes cause significant performance degradation. In addition, many TFs are required to improve the angular resolution, resulting in a large TF set size, which is a fatal problem for robots. So, various methods have been proposed to solve these two problems. The one is an online adaptation method. This method can prevent performance degradation by updating the TF set in an online manner. However, the TF set size issue remains. The second is an interpolation method. This method reduces the TF set based on Fourier series expansion instead of having many TFs for each direction. However, adaptation methods like the first method have not been explored for the Fourier series for the Fourier-based TF models. Therefore, this paper proposes an online adaptation method for Fourier-based TF models. The conventional TF models require multiple TFs for each direction, while the Fourier-based TF model interpolates the TF set based on the Fourier series expansion. Specifically, instead of having many TFs represented as H for each direction, fewer Fourier coefficients C are stored. The TFH is calculated using the Fourier coefficient C and the matrix of phasor function S to perform localization and separation. So now I will explain the proposed online adaptation method for Fourier-based TF models. First, sound source localization is performed based on the current TF. The localization accuracy is extremely important for the TF set update. So we used linear smoothing and outlier removal to minimize the localization error as much as possible. The normalized TF is estimated using the detected sound source using this equation. Then the current TF set is updated so that the difference from the estimated TF in the localized direction becomes smaller. However, since the Fourier-based TF model represents TF set by Fourier coefficients instead of keeping TFs for each direction, the difference for the corresponding Fourier coefficients C are calculated using these equations. Finally, the current Fourier coefficients C are updated with an adaptation rate. To verify the effectiveness of the proposed method, we conducted 3 experiments. In experiment 1, we compare the amplitude spectra of the adapted TF sets with those of the conventional method to confirm that the adaptation is correctly done. In experiment 2 and 3, we evaluated the proposed method on localization and separation tests using the standard deviation of the localization errors and the signal-to-distortion ratio. Additionally, we also compare the TF set size with conventional methods. This table shows the experimental setups. In experiment 1, a 15-channel microphone array was set up in a real experimental room. In experiments 2 and 3, we used a simulation environment with an 8-channel circular microphone array with third-order reflections using the image method. In experiment 1 and 2, white noise moved twice around the microphone array with a radius of 1.5 meters. And in experiment 3, male and female voices were convolved from different directions at a distance of 1.5 meters. For all experiments, the geometrically computed TF set was used as the initial value. First, we compare the amplitude spectra of the TF set after the adaptation in a real environment. Without the adaptation, the geometrically computed TF set was not updated, while the proposed method correctly adapted to the current environment, as well as the conventional TF model-based adaptation method. This table shows the evaluation results on localization task. Regardless of the TF model, the adaptation significantly reduced the localization error. The proposed Fourier-based adaptation method shows a smaller localization error than the conventional adaptation method. Additionally, this table shows the separation results. As in the localization task, the adaptation significantly improved the SDR. Furthermore, the proposed Fourier-based adaptation method showed significantly better SDR than the conventional adaptation method. This may be because the proposed method can use arbitrary angular resolution, while the performance of the conventional TF model is limited to a predetermined angular resolution. Furthermore, by reducing the Fourier order, the TF set was reduced with a slight performance degradation. This paper proposed an online adaptation method for Fourier-based TF models. The proposed method improved localization and separation by adapting the current environment. The performance of localization and separation of the proposed method were better than the conventional TF-based method. Furthermore, reducing the Fourier order decreased the TF size with a small performance degradation. Thank you for watching this video.